Good morning, and now I would like to present about introduction. As we look at the introduction slide, the roof of our engineering challenge begins with the challenge of the soft clay itself. Geotechnical, these soft soil deposits are highly hereditary because they are characteristic by the highest compressibility and low shear strength. Because the soil have very little capacity to support heavy load, it introduced several engineering risks. Specifically, it led to serious silting or differential settlement and a major stability issue both during the active construction phase and in the long-term post-construction period. Ultimately, the impact here cannot be overlooked. If left untreated, these conditions pose significant stability risks and cause long-term performance problem for embankment built on the soft deposit, potentially leading to the catastrophic slope failure or costly structural deformation. That's all for me. Now I would like to pass to my friend.
Hi, my name is Nunadira Ilyana binti Nazaruddin and my matrix number is CF240219. So today I'm going to present about application, which is soft clay soils treated embankment stability due to low strength and poor drainage. Therefore, this study analyzed effective stabilization strategies supported by real-world case study. So the first strategy that we look at involved geosynthetic encased columns or GECS. When soft clay lacks the strength to support heavy structures, GECs provide a reinforced foundation. The geosynthetic casing keeps the stone column intact, giving the soil excellent load bearing capacity while also improving drainage. The second method is deep soil mixing. Instead of replacing the soil, we improve it directly by blending the existing clay with cement or lime. This creates high-strength columns deep underground, which significantly increase the foundation shear strength and minimize long-term settling. So for our third approach is stage construction and preloading. Rather than building the embankment all at once, we construct it in phase. We apply temporary heavy weights known as surcharging, often paired with vertical drains to force the water out. This makes the soft clay compress and settle early, preventing unexpected sinking after the project is finished. So our final application is use lightweight fill materials and deep replacement. To avoid overloading the weak clay, we can construct the embankment using ultralight materials like EPS blocks. Alternatively, we can excavate the weak soil entirely and replace it with stronger granular materials. By applying these four strategies, we can safely and effectively build critical infrastructure on even the most challenging soil conditions. Thank you.
Hello, my name is Nathan Adinata Budiawan, number metric GF250020. I want to present slide methodology. Number one is study location. This study was conducted on a highway embankment project in Batu Pahat, Johor. The site consists of soft marine clay with low shear strength and high compressibility, which can cause settlement and stability issues. Next is a site investigation. 5 CPTU tests were carried out to a depth of 20 meters to evaluate subsurface condition, and the test provide data on soil layers, corrosion resistance, and pure water pressure, helping to identify weak soil zones. The next is laboratory testing. Laboratory tests were conducted to determine the properties of the soft clay. Fan shear test measured underneath shear stretch, while eudiometer test provide consolidation parameters. The next is analyze. The field and laboratory data were analyzed to predict settlement using Terzaghi consolidation theory and to evaluate slope stability through factor of safety analysis. The next is ground improvement. To improve soil performance, prefabricate vertical drainage or PVDS and surcharge preloading were applied to accelerate consolidation and reduce future settlement.
So basically, this study focused on a highway embankment project in Batu Pahat, Johor, when subsoil consists of soft marine clay do its low shock strength and high compressibility, soft clay can cause exercise settlement and stability problems. So, to investigate the site of condition, five penetration test with per pressure measurement or CPTU tests were conducted to depth of 20 meters. This test was used to identify soil profile, con resistance, and pore water pressure. In addition, laboratory tests were performed including vein shock tests to determine the undrained shock test and to obtain consolidation parameters such as the compression index, recompression index, and coefficient of consolidation. So basically, we collected data were then used to predict settlement using Takzaki one-dimensional consolidation. And to evaluate that slope, we stability through factory of safety analysis. Finally, we do ground improvement techniques, namely prefabricated vertical drains or PVD, yeah, something like that, and surcharge preloading were implemented to accelerate consolidation and improvement embankment stability. Thank you.
Alright, for the conclusion, the case study highlight the necessity of both laboratory and in situ method for evaluating embankment stability on soft clay soils. In Batu Pahat, the geotechnical behavior of soft clay was assessed using cone penetration test with pore pressure measurements (CPTU) and laboratory testing, revealing a thick layer of soft clay with significant settling and stability risk. Ground improvement techniques, including paste surcharge loading and prefabricate vertical drains, effectively mitigate this risk. A recorded settlement of 140 mm over 8 months aligned with design limits and reflected accurate soil parameter, leading to an improved stability factor of safety from 1.05 to 1.35, demonstrating the value of integrating CPTU and laboratory data for infrastructure development on soft clay foundation. That's all from us. Thank you.